Good evening, ma'am.
Yeah, good evening. So
Good
let's see
evening, ma'am.
last time, in last class, we were discussing the last thing that we did was topological sorting, right? So in topological sorting, and after that, we have a topic of longest path, which we do along the topological sorting only. So in topological sorting, we did this thing where we use this example, I guess. Some vertex, let's say.
Ma'am, can you give some revision of yesterday? Just give us live review.
Last time, I don't have the notes with me right now. The last thing we were doing was topological sorting. I can give you a recap of topological sorting.
No. Okay, ma'am. Let's continue. I know that.
Let's say you have this thing, and then you are going to have arrows of this. Let's have things in this direction. Let's take this thing. So I have this graph. Then the longest path. First thing that you do is topologically sort things, and then along with topologically sorting the graph, you can decide the longest path means that the longest path that you will be choosing to reach that point while you're topologically sorting things. So how do you do it? You start your just 1 second. So you keep track of when you're topologically sorting things, you keep track of the in degrees of vertices, right? So let's just keep track of in degrees. Let's write the in degrees on this side, uh, on the left side, and let's write the longest path till this point uh, on this side. So on the right side, we'll be writing the longest path. And on the left side, we'll be writing the in degrees of vertices. The in degree of this is 0. The in degree of this is 1. In degree of this is also 1. And the in degree of this is 2. No, 3. In degree of this is 3. Then in degree of this is 0. In degree of this is 1. This is also 1. This is also 1.
And
This is 0
then
again.
5 is 2.
Yeah, ma'am. In degree
The
of 5.
connection between 8 and 5.
We haven't we haven't
Like
decided
the
the direction of this, right? Wait, let me just
No, ma'am, 6. Sorry,
no,
6.
no, no, ma'am. The connection
okay,
between
it's
2
2.
to 5 and 5.
Yeah, it's 2 here, and let's then this is also 2. And then for 7 it is 3, right? And then we're done with all, right? So and then we'll write the longest path. So we initialize things with 0 only. Initializing means we just put 0 everywhere. Like let's just not write it everywhere. Let's just take the longest path till this point to be 0. Yeah, and let's say a starting vertex. So topologically sorting things, you can sort only from here, here, or here. So you can choose any of these 3 vertices. Let's do this one. Let's start with one only. So if you start from here, then first thing is you write the longest path till this point. And to find the longest path till all points, what you do is uh, you add 1 to the maximum incoming degree. So if this is like for this example, okay, let's just do it step by step. You have 0 here. Then you remove this thing. You have 0 everywhere. The longest path for every point now is 0. And then you remove this thing, this vertex, because you're starting your sorting from here. So the in degree of these two becomes 0. Let's remove these things first. The in degree becomes 0 here, and the longest path was 0 till there, and then
Ma'am, we will store 0 somewhere.
just 1 second. Just give me 1 minute. Just a second. Yeah. So we were doing. We had what was our graph originally? It was we had 1 here and 0, 0, right? So we had this thing. So and in degrees were 1 here. Then we removed this thing. So the in degrees becomes 0 here. We remove this too. And after that, for the longest path till 0, the initial, the 1 point was 0, right? Longest path was 0 here, and then you add 1 to it. So your idea is you add 1 to the maximum longest path till that point. So the maximum longest path till that point is written at the other vertex. So it's 0 here. So you add 1 to 0. So if you add 1 to 0, you will get 1 here. The longest path becomes 1 to this point, and on this point too, it becomes 1. And then you remove this one. And now at 0, you have these a lot of vertices within degree 0, right? This is 0. This is also 0. So a lot of these. So let's just start with this one. Then you go to this one. And then for this vertex, firstly you remove this one, right? You remove this edge. And then you add to the in degree, and then you change the in degree of this. So it was previously it was 3, now it becomes 2. And then for the longest path till this point is 1, right? And then you have to add 1 to the longest path till the last point. So the longest path till this point is 1, and you add 1 to it because you had like the path till here is 1, and then you just add 1 to it. So this will become 2. So longest path till here becomes 2. Then
Ma'am, I
and
really
you
want to
remove this
understand
thing.
this whole thing. Like we have just give the in degrees number, and then we will remove by zero by zero in degree.
You initially put the degrees. The in degree part is clear, right? That's the topological sorting thing that we're doing. We did it in the last class as well.
Yeah, in
With that,
degree.
we're trying to find the longest distance. So this is in degree 0. Here we have 1, 1. And then, okay, let me just write down the vertices here. 0, 1, 2, 3, 4. Or we'll write the vertices as they get sorted in the order, the topological order here. So we start with 1. For the longest distance means if you're starting from here, the longest distance till this point is 0 only, right? So you initialize with 0 only, the longest distance, and it's 0 everywhere. So you initialize with longest distance 0 at every vertex. And then you remove vertices one by one as per the topological sorting order. So you remove this vertex first. So first we do the topological sorting part. This becomes 0, this also becomes 0, right?
Yeah,
And then we do, so the longest path till 1 was 0, right? And after that, you're going one, like you're adding one edge to it, so it becomes 1. So each time you change this. Initially, it was 0. Initially, your longest path till every vertex was 0. But now, since you've removed this thing, it becomes 1. In short, you just have to add 1 to the last, or to the, if you came here from this vertex, so you just have to add 1 to the longest incoming path till this vertex. And the longest incoming path till this vertex was 0, right? So you just have to add 1 to this. That's it. Add 1 to this.
why would we add one to this? Because we will remove that so that in degree becomes zero, right?
We're not talking about in degree. This is the in degree. And this is the longest path.
So we will have to add one every initial point.
Yeah,
After
you add
removing
1 when you change the longest path. Let me just get done with this example. And if there's still doubts, then you can ask. We've just
Okay, ma'am.
started with it. You had 0 here. Its longest path was 0. Each time you get to another vertex. So if you, from this vertex, if you go to this vertex, initially the longest path for both the vertices was 0 because that's the initialization, right? Initially you had longest path of both the vertices 0, but then you move from here to here. So longest path becomes the longest path till the previous point, the previous vertex, which is 0 plus 1. So it is 1 plus maximum incoming longest path. It's in this one you, okay. So you get 1 here. And this gets removed. Then in the next step, you start from here because this has in degree 0, and you remove this thing first. The first thing that got, you started with 1, and the longest path was you took 0, and then you took 4. The next vertex that we're taking into logical sorting order is 4, and its longest path is 1, right? We're writing longest paths here. Its longest path is 1. Then you remove this vertex. Each time you remove a vertex, just write its longest path too, because that has been removed now, right? Initially, the in degree of 3 was 2. Now that you've removed the other vertex, it becomes 1, right? So this becomes 1. And the longest path here was 0 initially. But at 4, you had 1, right? Longest path here, you had 1. And here you had 0. So longest path becomes 1 plus the previous longest path, which should be 2, right? So you update this thing to 2.
Madam, how come the in degree became 1? Because it was 3. So it should be 2 right now.
We removed the other vertex, right?
Yeah, so we have to subtract 1, right?
Okay.
So 3 minus
We had
1 is
3.
2.
Okay. We had 3 here. Initially, this was 3. Now we have subtracted 1 degree, so it becomes 2.
Yes.
And then the path becomes 2. But we're not done with 3 yet because it's in degree. So you can only write the vertices here when you're in degree 0, right? When you're removing them. Then let's come to this one. So if you come to the 6th one, it has in degree and the longest path is 0, right? This will be 0 only. So if you start with 6, the longest path will be 0. And then you remove this thing. So this one becomes, it was this, right? So if you remove this thing, the in degree of this will change. This will become 1. And we had 0. Longest distance for 5 was 0 initially. And then when you change this longest path, this becomes 1. Longest path till 6 was 0. And then you add 1 to it. So you get 1 here. Then you have this to remove and this to remove. So let's remove 10. So if you remove 10, the longest path will change here. So you add 1.
Ma'am, I have a doubt.
Yeah.
Yeah, so how we remove these numbers? Like first we remove 1, then we remove 10. How we consider that we should remove this or that?
We've done this in topological sorting. The one with 0 in degree gets removed.
Okay,
If
we'll
anyone
start
has,
with 0 degree.
you can choose any one of these to be removed. You can remove 2 or 10. I'm choosing to remove 10 first. And then I'll come to 2.
Oh, so we will remove in the order of in degrees.
No, the one that has
In the
0 degree gets removed. That's all.
okay, ma'am. Got it, ma'am.
Okay. Then you remove this thing. The longest path till this point is 0. And then if you'll add, so it was 0 here. And if you'll add 1 to it, it will remain 1, right? So you have to take the maximum of it, I guess. So you should be keeping it as 2 only. The graph that we've chosen is actually very complicated. So if you remove this thing, the in degree obviously decreases to 1. This decreases to 1. And then for this one, we're not changing the longest, this thing. The longest path we're not changing for 3 because it's already 2. So, and from here you're getting 1, right? I think we choose the minimum of these two. So it should become 1 then because you had 0 here and then from here you had 1. So the longest path then becomes 1, I guess.
No, ma'am, we choose the maximum.
The maximum of the incoming ones, right?
Yes, ma'am.
Maximum of this one and the one that's incoming. Okay, so it's 2 already here and initially we had the point here was 10 and the in degree and the longest path both for 10 was 0. So it remains 2. Yeah, because we're finding the longest path, right? So let's keep it 2. And next up, we remove this one. 10 got removed that it had longest path 0. And then 2 gets removed because it has 0 in degree. And the longest path for 2, it was 1, right?
Yes, ma'am, it will be 1.
Yeah. Got to mention it here. It was 1 because there was just one incoming edge. Okay. Then you remove this thing. So the in degrees change first. This becomes 1. No, this is not in degree, right? This becomes 0. this becomes 1, and this becomes 0. And this becomes 2. Then you remove these edges. And for the longest distance, we had an edge here. We had an edge previously here, right? And we've removed it. So the longest path till this was 1. And here you already have, so you add 1 to the incoming one. You add 1 to the incoming longest path. So this is, the longest path till here is 1. If you remove this edge, you add 1 to this. So this becomes 1 to this thing. This thing. So this becomes 2 here. And then for this one, the longest path is 1. So it again becomes 2. For this one, the longest path was 1. So this again becomes 2. And then you remove this thing. Now the in degree of this thing is 0. So the longest path for 2 was 1. When we removed it, we had 1 here, right? The longest path was 1. So we have 1 for this. And then for the longest path for 5. Next up, we take 5 because it has in degree 0. And the longest path for 5 is 2. Let's write it down.
Ma'am, 3 also have in degree 0. Why would
Let's
we
take
not
3.
consider 3?
I've already discussed this in the previous class. If you have 2 vertices with degree 0, you can choose any one.
Mm.
Let's take 3. So now if you remove 3, the degree here becomes 0. And the longest path becomes, so the longest path till this is 2. So you'll add 1 to this thing. This becomes 3. You add 1 to the longest path till the last vertex. So the last vertex is this. You add 1 to this.
Excuse me, ma'am.
Yes.
Ma'am, in 3, why we left it to 2? Why we did not add 1 plus max of incoming? So it is max is 2. So why we didn't add 1 when we remove 10?
Was 10 connected to 3?
Yes, ma'am.
Just 1 second. What was our, let me just, original graph was
10,
1,
3
4.
had incoming edge from 10.
10 had the
It had an
longest
incoming
path
edge,
0.
no? We didn't
Yes,
have
ma'am.
this edge. 10's longest path is obviously going to be 0 only because it has no incoming edges.
Oh, yes, ma'am.
We had an edge from 3 to 10,
Acha,
not 10,
okay,
10
so
to 3.
longest path for that was 0. For 10 was 0,
Yeah.
so we didn't add.
Because it
Okay.
has, 10
Okay,
had no incoming edges, right?
yeah, okay, understood, ma'am.
Next up, we remove 3. So longest path till 3 is 2. And then we remove this thing. We've made changes to 9, right? So we remove this thing. And then you can take up 9 next. So if you take 9, its longest path is 3. So you can write 3 here. And then remove this thing. Then coming to this one, next up you take 5. The longest path till there is 2. Then you remove this and this. In degree here becomes 0. Here it becomes 1. And so the longest path till here is 2. And now if you add 1 to 2, you'll get 3. So the longest path for here, for 8 will be 3, right? So for 8, it's 3, which is 1 plus 2. 1 for this edge and 2 for this. So you get 3 here. And then the longest path of this also gets updated, right? But this becomes,
Sorry to interrupt. How we decide that this is the means 5 should be means 8 should be 3 degree 3, because here is 2. I can say that the 2 outgoing path, right? How can we say that it is 3?
This has nothing to do with the degree. This is the longest path. The longest path till this point was 2, and now you're adding an edge to it, so this becomes 3. That's the idea. Because we're going to remove this edge. We're going to remove this vertex 5, and we're going to remove every edge that is outgoing from this vertex 5.
Why we cannot add 7?
Add 7 to what? What's your question?
She is asking, I think that why did not we change the longest path of 7?
Yeah, but we're going to change that. So you first remove this thing, and for the longest path for 7, you take. So this already had 2, and now you'll have 3, 4. So this becomes 4. What you do here is actually you had 2 here, right? So you had 2 here, and 2 is here. So you add 1 to this 2. You do 2 plus 1. So either you take 2 or you take 2 plus 1, 3. So you take 3 here because this is the longest, right? So we update this 2 to 3. And then I'm not doing it because I'll remove it at the end to avoid confusion. Is this clear? This is when you remove this entire thing. Is still this part clear to everyone?
Got it.
Okay. And then you remove because we've done all the things that we needed to do after removing this. So then you remove the vertex 5, and then you're left with these two. This is 0. So you write 8 next. The in degrees, the longest path is 3. And then you remove this thing. So the longest path till here is 3. And then it's 3. So you do either 3 plus 1 or 3. And the longest out of these two is 4. So you should be taking this. 4, right? So for 8, you have 3. And here you change the in degree. Because after removing 8, you will be left with in degree 0 for 7. And the longest path, you have to take the maximum between 3 plus 1 and 3. So it will be 4. And then finally you remove 7. And the longest path for that is 4. Is this okay to everyone?
Yes, ma'am.
Yes, ma'am.
Okay. So,
Ma'am,
should
can
we
we
take up
see
one
one
more?
more example of this question? Like another on this topic.
Madam, is it possible to take some simple example, like rather than taking 10, some 3, 4 vertex, so it will be simple.
Okay, let's do it with 3, 4 vertices. Is that okay?
Yes, yes.
Okay. So let's do 1, 2, 3. So let's do this thing, this. Let's do this. The in degree of this is 0. In degree of this is 0 as well. In degree of this is 2, right?
Ma'am, 4
1,
is
2.
1 in degree.
Yeah, we have an incoming edge. Then it will be a cycle, no? Then we can't topologically sort it. I've changed this edge because then if I would have taken it to be this edge, then we can't topologically sort this graph. That's why I've changed the direction of this edge. So 0 for this, and then 0, 2, 0. And for 3, you have 2 in degree.
Ma'am, the in degree of 2 would be 3, right?
Yeah. Then you take the longest path. So if you're starting with this vertex, let's say we're starting a topological sorting from 1. So this is 0, right? The longest path for this is 0. These are vertices, and then you have longest path here. So you first remove 1. When you remove this thing, this degree becomes 1. This degree becomes 2. And then for the longest path, it becomes 0. The longest part till here is 0, and then 1 for this edge, so this becomes 1, and 1 for this edge, so this becomes 1 as well. And then you remove this thing. Then next, because this has in degree 0, so let's take 4 next. Longest path is 0 only. And then for this one, you do 0 plus 1, so this will be 1, but we already have 1 here. So either you take the maximum of the degree that's already there, not degree, the longest path. Sorry, the maximum of the longest path that's already there, that is 1, and the one that is coming from here. So from here you're getting 1, 0 plus 1, 1. And from here you have 1 already, so you should be taking 1. This remains 1, no change here. So we keep it as 1, and for this one, the longest path here is 1. And if you add this thing here, you'll get 2, right? From here, you'll get 2. And you have to take the maximum of 2 and 1. 1 we get from here, and 2 we get 1 from here, right?
Yes, ma'am, we will
It's the
get
same
1.
case as, it's the same case as this vertex. So this also, you get 1 only. And then you can remove these edges in this vertex. And then after this one, and the in degree here becomes 0, right? This in degree becomes 0 and this becomes 1. Then you take this one up, third, and the longest distance for this is 1, right? And then you remove this. So the longest distance here is 1, which it already has. And then from here you get 1 plus 1. This plus 1, right? So you get 2. And the maximum then will be 2. So you take maximum 1 plus 1 and 1 for this vertex, for the longest path of this vertex. So you get 2 here. And the in degree becomes 0. The longest path for 2 becomes 2. Is that okay?
Yeah, okay, understood.
So madam, we
no.
have to choose the maximum of like the current degree and what we are bringing from the
Not
vertex.
the current degree, the current longest path. The longest path
Ma'am,
for that vertex. Yeah.
when we see the diagram path or direction, can we assume that to see that this is the longest path for the reference we are doing correct or not? We'll do the calculation, but to see the graph, can we say that this is the correct answer?
I
Means
don't
like,
think
is
I
there any
understand your
way
question.
is there any other way to understand the graph?
So this, to find the longest path, this is the only way that's there.
Because I watched the professor video as
Yeah.
well, and I attended the session, but still I'm not able to understand that how to do this.
What was our graph originally? This, right?
Ma'am, I am also a little confused in like when we are updating from
Okay. The
adding and
longest
when we are
path,
not adding.
not
Because
adding. Okay. You just have to take this thing, 1 plus maximum of the incoming degrees, or you can just take 1 plus the incoming degree. Just simply take 1 plus the incoming, not degree. 1 plus incoming longest path. Incoming longest path is this that you write. So if you have 2 here and you're removing this thing, let's
Ma'am,
not take this
from
one.
where to
Let's
where
take
we
this.
have to means search the longest path. Means here is 1, 2, 3, 4,
Longest path
and
means you've started from 1. That means if you start the longest path in topology, that means your longest path in topological sorting. So no matter in what order you logically sort these things, you can start from 4, then 1, then 3, then 2, or you can start with 1, then 4, then 3, right? The longest path for both of these is basically you're going to get 0 only for both of these because they're interchangeable, and then for this one, which actually means there's no way to reach this point. If you start from 1, you'll have to use at least 2 edges. 2 edges for 2. That means 1 and 2. That's your longest path. That's the longest you can go. Now, if you want to exceed things, you can't exceed them. But if you had this thing, let's say you had this thing here, then your longest path for 2 will become this, this, and then this. So it will be 3 then.
Why cannot we reach 3 to 2? Why we need to go to 4?
You can reach from 3 because you're calculating the longest path, right? That's what longest path means. That's the longest you can go. That's why we're taking the longest route to reach 2.
So according to the graph, I can say that we will take 3 edges. Vertex means we need that.
What?
To reach 2, the longest path will be 3.
Yeah, because if you do it, you start with 1. So you'll what should we do for this one as well? You start with 1 obviously, and then for this one, so the integer, then you will remove this thing, and the longest path till 2 will be 1, and 3 it will also be 1. So for both of these you'll have 1. Then you'll remove one of them. Then you will take up next 3 as next. You'll have 1, 3, and at 3 the
4.
longest path is 1, right? This is 0, this is 1. And at 2 it will become, now at 2 your longest path will become 2. And at 4 your
Are
longest path will become,
matrix this 1 3 2 0 1 2, we are making the matrix.
no, we're not making any matrix. Let's do this example too for you to clearly understand things. What do you not understand anything in the algorithm? Is there anything that you don't understand in the algorithm? Let's not get into why are we doing, what are we doing. You just have to know the algorithm. Is everything in the algorithm clear to you?
Yes.
That's enough. That's what you have to do in exam. Let's move to the next topic then. I hope the longest path algorithm is clear to everyone.
When you are converting the power degree 0 and 1 and 2 3, that is confusing. That part is confusion. Means how you do this vertex and means you are changing the degree power 2 to 3 1 to 2 and you are deleting that the previous one. That is the confusion.
That is topological sorting. We've already done it in previous classes.
Okay.
Okay. So coming to the next topic.
Ma'am, one thing, do we
Yeah.
start from the maximum connected vertices, right?
Maximum. No, we don't start from, we just start with the vertex within degree 0. That's all.
Oh, okay, ma'am, understood.
Okay. The next thing we have is transitive closure. So for transitive, I hope everyone knows what a transitive relation is.
Yes, ma'am.
Yes, ma'am.
Yeah, ma'am.
Okay, a transitive relation basically means if you have A related to B and then B related to C, then A should be related to C. Now, if you look at it as a graph, let's say this arrow represents that A is related to B. That means that A is related to B. Then we have an arrow from A to B. Now, if that graphically, mathematical, in relation terms, you mean this thing. If A is related to B, this is for related. If A is related to B and B is related to C, then A should be related to C. That's your transitive relation, right? And graphically, if you make graph here, then if there is an edge from A to B, there is an edge from B to C, then there should be a direct edge from A to C. Or in simple words, if you have a path from A to C, then you should have an edge from A to C. That's the transitive. So if you've been given a graph G, then the transitive closure we denoted by this thing. The transitive closure of this graph is basically a graph which is like you make the graph of G only, but you make sure that your graph is transitively closed. Transitively closed means that if you have an edge from A to B and you have an edge from B to C. So if AB, BC, Or in simple words, if you have a path from, let's say, A to F, then there should be an edge from A to F.
Ma'am,
Is
it
it clear?
Means F is reachable to A.
What? I couldn't hear your question. Can you repeat it?
ma'am, it means it should be true for every vertex.
Yeah, it should be true for every vertex, every path. So if you have a path from any vertex to any other vertex, then there should be a direct edge, or we don't need the word direct here. There should be an edge from this vertex to this vertex. So if you have a path from A to F, that means if you have A to B, then B to C, then C to D, then D to E, then E to I, then I to F, then there should be a direct edge from A to F in the graph. Is that fine?
Okay, ma'am.
That's the transitive closure of your graph. It's represented by this G plus. So if
Ma'am,
G
the
is your graph, G plus is called the
necessary
transitive
that
closure.
B and C.
What?
Ma'am, can we say that initial point is always connected with the final point in the graph?
What's an initial point and what's a, there is no
Like
such thing as initial
A is
point and final point.
like A is the with the 0 in degree, and the we just go to the final point, that is the last vertex F. So we have to connect A and F.
That's what I've written here. If you have a path from A to F, does everyone know what a path is?
Yes.
If you have a path from A to F, then you should have an edge from A to F. That's it. That's all. That's your definition for transitive closure. So if you see a path between any two vertices, let's say Vi, Vj, these are any two random vertices in your graph G, then if you see a path, let's say this is Vk1, this is Vk2, this is Vk3. If you see this thing, then there should be a direct, if you have a path to go from Vi to Vj, then there should be a direct edge from Vi to Vj. That's all. And that should be true for every vertex present in your graph. Is that okay? That's transitive closure. And then,
Ma'am, can we say that it's like a cycle where the last node connecting the initial vertex has a back edge kind of thing? Opposing.
you don't have to involve edges and all and back edge forward edge. You don't have to get into all that because you wouldn't need that here.
Ma'am, is it like an edge is directly and indirectly connected to other point?
It simply means if you have V1, V2, V3, and if you have this thing, and let's say you have V4 here too, that means because V1 is connected to V2 and then V2 is connected to V3, there's a path from V1 to V3. That means you should have a direct edge. So let's say this is your graph. So to draw the transitive closure of this graph, you should be doing this thing. There should be an edge from V1 to V3 because you have a path from V1 to V3. Then there should be an edge from V1 to V4 because you have a path from V1 to V4. So there should be a direct edge. And then you should have an edge from V2 to V4 as well because you have a path from V2 to V4. This should also be a thing. Is anything left?
Ma'am, then can we say that each edge is connected to the last point?
Each edge, we are connecting vertices here.
Yeah, so the thing is that each vertices is connected with the endpoint, that is the last wedge in this example, like V4.
Yeah, like V4, but we also have connected V1 to V3, and that's not the end vertex, right? There's no such thing as end vertex as per the terminology used in graph theory. But if you're taking this thing V1, V2, V3, V4 as a path, and then you're saying you should be connecting V1 to V4, that's right, because this if you're considering this as initial point, this is final point, you should be connecting this to this. That's
Ma'am, in
fine.
this example, we would also connect V1 to V2, like V2 to V3 and V3 and V4. Both are connected, right?
Yeah.
Okay.
It's not about the final point and the initial point. Yeah.
Ma'am, so transitive closure.
What?
What is transitive closure?
We just discussed the definition here. If you have a graph G, then the transitive closure of your graph is basically you make it transitively closed. How do you make a graph transitively closed? If this is your graph and you have a path from V1, Vi to Vj, then there should be an edge from Vi to Vj. This is a simple definition. If you have G as graph, then G plus the transitive closure of G should be transitively closed. That means if if there exists a path from Vi to Vj, this is a symbol for there exists a path to Vj, then there should exist an edge from Vi to Vj, or you can say then Vi Vj should be an edge in G plus. Is this okay?
Yes, ma'am.
This is the same as transitively closed. Then is when you say that your G, if that happens, then you say that your G plus is transitively closed. That's all. Can we move to the next topic?
Yes, ma'am.
Okay.
Yeah, ma'am.
Then let's say you have a graph G, and corresponding to that graph, you can make the adjacency matrix, right? So let's say the adjacency matrix is A. And if you have Aij as 1, what does that mean? Aij means ijth entry of A. If Aij is 1, what does that mean?
In degree of J is 1.
I hope everyone knows what Aij is. Aij is the entry, the arbitrary entry in the matrix A. This is A11, A12, So if this entry, or not this entry, if this entry is 1, let's say A12 is 1, what do we mean by this? What conclusion can we draw from here?
1 and 2 are connected. There is an edge between 1 and
Edge between 1 and 2, yes.
And let's say we are talking about directed graphs, then what does it mean?
There is
That there is an
One to
edge
two.
from 1 to
Looking
2.
at 2.
Yeah, there is an
There's an
edge
edge
between
from
1 to
vertex
2.
1 directed towards vertex 2. This is what it means, right? So this is for your A graph. Now when you do it for A square, so it simply means that you have a direct edge from V1 to V2. If your A12 is 1, it means there's a direct edge from V1 to V2. Now if you have A square and then you are taking the ijth entry of this, or let's say you're taking the 1, 2 entry of this, that means you first squared the A and then you're taking the 1, 2th entry of A square. So if your A square is this, let's just write it as B11, B12, B13. If this is it, then this is the B12th entry of A square, right? Now, if this is 1, what does that mean? Here it means, here you had a direct edge from V1 to V2, right? In this case, it means that from V1 to V2, you have an intermediate vertex, let's call it Vk, and then you have this thing. That means there's at least one vertex Vk such that there's an edge from V1 to Vk, and then there's an edge from Vk to V2. Now, if you have A cube 1, 2 as 1. Now, if this is 1, this means that from V1 to V2, there are two things here, Vk and Vj. There are two vertices in between V1 and V2, such that you have a path you have this path. Is this okay? That means you have a path of length 3
V2 reachable
from
from
V1 to V2.
V1 and we have two vertices between them. Does
Yeah,
this
two
make
vertices between them for this one. And this is for this one.
Power shows edge.
Yeah, powers are the edges. You can say the edges between them, or you can say the length of path. So if this is the path, then the length of this path is 3, right?
Yes, ma'am.
So A, if you have the 1, 2 entry of A cube is 1, that means that there is a path of length 3 from V1 to V2. At least one path of length 3 between V1 and V2. Is that okay?
Yes, ma'am.
And then while multiplying things, because all the entries in A are of either 0 or 1, right? All the entries in A are 0, 1. So when you multiply things, you do two things in matrix multiplication. One is you add things, and then the other one is you multiply things, right? So let's see all the possibilities for multiplication addition. If you have 0 plus 0, the plus is basically it's for all. So if you have 0 and 0, you get a 0 here. If you have 0 plus 1 or 1 plus 0, you have a 1 here. If you have 1 plus 1 here, that's also 1. Now, why are we doing this thing? Because you have plus is basically for all. That means if you have 1 in either of these, if you have 1 here or here, then you will have 1 in the final answer. Otherwise, you will have 0. So you want 1 in one of these places, right? If you have 1 plus 1 plus 1, then it should be 1. Because you want 1 in one of these places and you have 1 in one of these places. Now, if you do 0 plus 1 plus 0, that's also 1 because you want 1 in one of these places which you have. If you do 0 plus 0 plus 0, then you'll get 0 because you wanted 1 in at least one of these places. Is that okay?
Yes, ma'am.
Yes, ma'am.
So it can 0 or it can 1.
Yeah, it can be 0 and 1 only. And then in the multiplication part, your multiplication is for AND. That means if you want 1 in the final answer, it should be 1 here and 1 here. Then it will be 1. Is that okay? That means if you
Yeah.
take 0, 0, you will get 0. If you take 0 and 1, you will get 0 again. If you take 1, 0, that's 0 again. If you take 1, 1, you will get 1. If you understand this thing for graphical use, it means if you have an edge from V1 to V2, we take 1 2th entry, A1 2 as 1, right? Now, if you have V3 here, then we should be taking V23 as 1, right? A23. That means for you to have an edge from V1 to V3, you should have an edge from V1 to V2. That means A12 should be 1, and you should have an edge from V2 to V3. That means your A23 should be 1. So this is AND, right? And let's say you have V4 here. Now, if someone asks you, what's your A13? Then it's 1, right?
Square, ma'am. A square.
Yeah, A square. What we're doing here is we're doing this for a path. If you have a path. So that means if you have a path from V1 to V3, let's say you have to find if there's a path from V1 to V3. Then you start with V1 to V2 and V2 to V3. You'll have a path from V1 to V3 if you have a path from V1 to V2 and a path from not a path, an edge. If you have an edge from V1 to V2 and an edge from V2 to V3. Or an edge from V1 to V4 and an edge from V4 to V3. Right? if you want an edge from V1 to V3, then either you should have an edge from V1 to V2 and V2 to V3, this thing. Not edge exactly if you want these to be connected, right? Or you want this thing. So your AND gets replaced with multiplication and your OR gets replaced with plus. This is what we do when we multiply matrices. So when you do A square,
Okay.
when you do A square 1, 2, let's say you're doing A square 1, 2. Or let's take a random thing, let's take ij. So if you're doing A square ij, this means, now in A square ij means, what do you do in A square ij? You write A here, then A here, and then you multiply the ith row of this A with the jth column of this, right? And then you add them. So if you are looking for A12, and this is your matrix, A12, A11, A12, A13, and I'm not writing the entire matrix, and same you do here, right? Because you're multiplying them twice. This is your A square, this entire thing. So for this entry, you take the first row of this and the second column of this, right? And then you do A11, A12 plus A12, A22 plus A13, A32, right? This is what you do for your A square 1, 2 entry. So now if you want a path from, this means a path of length 2 from I to j, right? For this you would want either this you want as 1, right? If you want a path of length 2 from 1 to 2, you want this entry to be 1, correct?
Yes.
So in this case, now how do you get this? Either you want this thing 1, this term 1, or you want this term 1, or you want this term 1, right? That's why I was saying your plus is replaced with, it's replaceable with or. And for this to be 1, for A11, A12 to be 1, you want A11 to be 1 and A12 to be 1, right?
Yes, ma'am. Because we are multiplying.
Yeah, because if any one of them is 0, then the final answer will be 0. There's the Boolean multiplication here. If any one of them is 0, that means you're going to get 0. That's why you want both of them to be 1. But that's not possible because your A11 is always 0, right? This is always 0. That means you're going to get a 0 here. A22 is also always 0. This is also 0. Now you have only one possibility left. That means A13 and A32 should be 1. That means your A13 should be 1 and A32 should be 1. If you want this thing to be 1, that means there should be a path, there should be an edge from 1 to 3, vertex 1 to vertex 3, and then from vertex 3 to vertex 2. Does that make sense?
Yes, ma'am. Yes.
Okay.
Ma'am,
Ma'am,
metric multiplication in this is not similar what we have studied in mathematics.
No, it's similar only. You're multiplying when you take AB, and let's say you're multiplying AB, and then after multiplying, you're taking the ijth entry of AB of this matrix. Then what do? You take the ith row of this and jth column of this, right?
Ma'am, in mathematics, we take the first row and first column of.
First row
What, ma'am?
and second column.
No, first row and first column in mathematics. In
For
ma'am,
this entry, this is 1, 1 entry, right? 1, 1th entry of AB. You take first row of A and first column of B. This is what you do, right? If you have this as A, this as B, and this as AB, then for this entry, you take first row and first column. and then you
Yes,
write,
ma'am. Yes,
multiply
ma'am.
this thing with this, and then you add them and write it here. So for your AB11, you should be taking A11, then B1, you do this thing, right? B11, and then A12. So that's what we've written here, right? We've done the same thing here. That's what I said. First row, for 1th entry, you take first row, first column. For 1th entry of AB, you should be taking, for this entry, you should be taking first row and second column, right?
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
That's the same thing we have done here. Matrix
Ma'am, can we
multiplication
see one?
remains same. What?
Yeah. Can we see one question on this topic?
There are no questions as such on this topic. These have been discussed in your lectures as this only. What does your A square represent? What does your A cube represent? They have been discussed in this manner only.
So, ma'am,
Please help in other questions. They don't have questions of their own, as far as I can
okay,
see in the assignments and everywhere.
okay.
Okay. So for the A square ij thing, if you do ij here, you should be having AI1, A1I, 1j. Actually, you have j here, right? This thing plus A. These things remain same. You change these things. Plus so on till A. I think we take this thing till n minus 1. This is the general formula. It's exactly the same as what we've written here. And then this was all about the matrix multiplication that we do, and because in later algorithms, the algorithm that we study, we'll be using matrix multiplication there. That's why you should know what matrix multiplication is and what do we mean when we say A square ij is 1. Okay. Coming to, then we'll discuss the minimum cost spanning tree. Before that, we'll discuss spanning tree. Spanning tree of a graph, minimum cost spanning tree, and then 2 algorithms to discuss minimum cost spanning tree. And then we'll come to Dijkstra and all. Okay. So for spanning tree, your tree is basically it's connected, and it's connected in such a way that even if you remove one edge, then it's no longer a connected graph, right? So it's a minimally connected graph. That's the definition for tree, right? So a spanning tree is basically, let's span, that's a tree. The spanning tree should be a tree first, and then it should be spanning the entire graph. So let's say if you have this graph, V1, V2, V3, V4, then your spanning tree is basically a tree which spans this entire graph. Spans in the sense it connects, it's a spanning tree, it's a tree plus all vertices covered. That's a spanning tree for your graph. So if you have this graph, then your spanning tree could be this.
Ma'am, in this graph, edge does not have any direction.
But that's fine. And while discussing the spanning trees, we don't use it for directed graphs. So spanning trees and minimum cost spanning trees are only for directed graphs. For undirected graphs, we don't do it for directed graphs.
Okay, ma'am.
Ma'am, all vertices covered means?
All vertices covered means you should have every vertex in your spanning tree. That means if you have this thing, V1, V2, V3, V4, and then you have this.
Is there
Now you can
BFS
leave one of the
used or
vertices, right?
DFS is used, or either both of not used?
Firstly, when I'm answering one question, there's no point of asking another and posing another question, right? Let's get done with the question at hand already. So someone was asking about what was someone previously asking? There was
Ma'am,
some business here.
what was all vertices covered means, I asked.
Yeah, all vertices covered means you should have all vertices in your tree. Now, if I do this thing, V1, V2, V3, now technically this is also a tree, right? This is a tree, but it doesn't
Yes,
span
ma'am.
this graph because you have one vertex missing here. That vertex should be here. Is that okay?
Okay, ma'am. Okay.
Okay. Does anyone have
Ma'am,
any
can
other
you
doubts?
explain it again?
There is nothing to
Ma'am,
be
can you
explained.
explain it again?
It's just a small definition what a spanning tree exactly is. So it basically is a tree. I hope you know what a tree is. Do you know what a tree is? It's a connected graph. It's a minimally connected graph. That's your tree, right? So if I draw a minimally connected graph here, I can also take V1, V2, V3. Now this is also a graph and it's minimally connected. This is a tree, right? But
Yes,
we have
Yes,
put
ma'am.
ma'am.
one more condition here, which is all vertices should be covered. That means I want all the vertices that are there in this graph to be present here. That means I want V4 here in this tree. Then is when I'll call this a spanning tree. And if you, uh, is that okay?
Yes,
Ma'am,
ma'am.
I have a doubt.
Yes.
Is there BFS or DFS be used or not?
Have we discussed DFS anywhere yet? If we haven't, that means we're not going to use it and we don't need it.
Okay, ma'am.
Okay. Coming to the minimum cost spanning tree. So when you do first we discuss, let's just discuss weighted graphs first. So weighted graphs are so far we've not studied anything where edges have weights. So if you put weights here, weights means just number here. That means it could be anything. Let's say if this is distance, then it could mean that this is 3 kilometers, this is 2 kilometers, let's say this is 1, this is 4, this is 5. These weights that you put on the edges, these are weights on edges. These could be anything. Now in this case, we've taken them to be the distances, or in, let's say you have a flight from here to here, so these could be a cost as well. This could be from here to here you need 3K, and from here to here you need 2K. So these weights could be anything. These are called weighted graphs, and weights sometimes are taken negative too, but we're not getting into the negative part yet. So, and for the spanning tree, now and then we discuss minimum cost spanning trees. So for minimum cost spanning tree basically means that you obviously need a spanning tree from here. Let's say this is 6, but you need to make sure that your cost comes out to the minimum. That means the total number that you take. That now if you want to take a spanning tree from this one, there could be different ways to take it, right? Someone can take V1, V2, V3, V4. Someone can take this, while someone else can take V1, V2, V3, V4, right? That's also fine. Someone else can take V1, V3, V4, and V2. This is also possible, right? So there are a lot of spanning trees. These all are spanning trees, but we want the minimum cost spanning tree. Minimum cost means your sum of weights should be minimum. So if you have 3 here, 2 here, 4 here, the sum comes out to be 4, 2. So it's 9. In this case, it's 9. This case, it's 10. No, 11. This one, it's even more, I guess, 12. So out of these, the minimum is this, right?
Yes, ma'am.
How do we, so obviously we need to have a proper way to find the minimum. We can't just be drawing every tree, every possible spanning tree, and then find the values and then see which one is least. That takes a lot of time. So for that, we have algorithms. This is called the minimum cost spanning tree. So the one that has minimum cost, minimum total weight is called the minimum cost spanning tree. How do we find the minimum cost spanning tree? We have 2 algorithms for it. First is Prim's algorithm. For Prim's algorithm, let's take a nice tree first. Shall we take this only? But it's let's take this. Let's take the weights to be 1.
And we also repeat numbers, also repeat weights.
Yeah, you can repeat weights. I've repeated it.
Okay.
Okay. So in Prim's algorithm, you start with the 1.
Ma'am, in
the
middle,
edge that is
6, 5.
1, 0. No,
Madam, should we also connect 1 and 4?
then
2 and
4.
3?
1 and 4 is not connected, right? In the original one.
And 3 and 7. I mean
3
weights.
and
3
7.
and,
The weight for 3 and 7 is 5, right? We've written it.
and 5 and 6.
Okay, yeah, this 5 for both. Let's take 5 for
Okay.
this, 4 for this. 4 and 5. In Prim's algorithm, you start with the edge that has, because you have to find minimum weight, we start with the minimum weight edge, which is this edge, right? We start drawing the tree here. We keep this edge. We give it as minimum weight. Then we take the next edge that has minimum weight. The next edge that has minimum weight is this edge or this edge, right? Let's take this one, 2, and let's take this one, 2. So in simple words, you have to take edges in ascending order of the weights. So you started with this one, you take this one first, then you take this one, then you take this one. But just make sure, because we have to find the minimum cost spanning tree, right? We're looking for minimum cost spanning tree. So we need it to be a tree. For that, we just need to make sure that every edge which creates a cycle should not be there, right? So let's say you started with 1, 2, and let's say you have 2 here. Then you shouldn't be choosing this edge, because this will make a cycle. Then it won't be a tree anymore. And we're trying to find the minimum cost spanning tree. So to make a tree, we need to make sure that there are no cycles.
Okay,
You
ma'am.
shouldn't be, either don't consider this edge or don't consider this edge. Now, if this is 3, then which edge should then I should definitely not be considering this edge, right? If this was 2 and this was 3, then I should not be considering this edge, right? Is this clear to everyone?
Yes,
Ma'am,
ma'am.
ma'am,
Yes.
ma'am, when we took the both weight to be 2, so is there any convention or any weight so that we would have to choose the lowest vertices first or the next or the highest
No.
vertices first?
There's no convention as such. If you have if both the weights are equal, you can choose any edge, but just make
No,
sure
no,
that edge is not a closing edge or a cycle.
no, ma'am, like 1 and 3 and 2 and 3, if assume both are 2, so
1 and 3 and 1 and 3 and
2 and 3 both are 2.
okay.
So do we have to choose which one should
No.
we choose first, 1 3 or 2
Choose
3?
anyone. You
Anyone.
can choose anyone. Yeah.
Okay.
This
Ma'am,
case,
I
because
have
this
one-
was 3, we've chosen this.
Ma'am, just one thing. Ma'am, when you are starting from the vertices, I mean, basically the question will be given in such a way that we have to select the longest path and in the lowest cost, right?
No, you don't have to find the longest. Our main idea is to find a tree. So firstly, it should be a tree, a spanning tree. That means a tree that covers every vertex. And then it should be of minimum cost. Minimum cost means the weight of edges should sum up to the minimum thing. So for that, we start with the minimum weight edge. That's why we start with the edge that has minimum weight.
Okay, ma'am. Got it.
It has nothing to do with longest path.
Okay, ma'am. Thank you.
Every
This is one.
vertex should be present in.
Yeah, because it's a spanning tree, every vertex should be present in the tree. Okay, then next up, the next least weight edge. What's the next least weight edge? These, right? 2, 4, 1, 3.
2 to 4.
There are a lot. This one, this one, this one, and this one. So let's take 2, 4. Now we can't take this one because then it will be a cycle, right? We have to avoid cycles. That's why we shouldn't be taking this edge. So we skip this edge. This has weight 3. Then this also has weight 3. So let's draw this edge too. 5 and 7. So this has weight 3. And this has weight 3 as well. So let's keep this one too. Then coming to the next least weight, which is 4, right? So it's this edge and this edge. Now you can't take this edge. This edge though has weight 4, but it's a closing edge for a cycle. So you shouldn't be taking this edge. And then this edge is also it's also contributing to a cycle, right? So this becomes a cycle. So to avoid a cycle, you should be avoiding this edge too. So we're not keeping these two edges because they are forming cycles. This edge and this edge. And I think we've found our every vertex has been covered, right? Except for this one.
No, yeah, it is.
That's it.
It is
Every
not.
vertex has been covered, and this is a tree. That means we have found our minimum cost spanning tree. So this is using Prim's algorithm. Is this clear to everyone? Very simple
Yes,
algorithm
ma'am.
it is.
Yeah, ma'am.
Yes, ma'am.
Okay. Then we come to the next algorithm, which is Kruskal's algorithm. In Kruskal's algorithm, let's just take the same graph and try it with Kruskal's algorithm. So I have 1 here, 2, 3, 4.
And 8.
This is 3.
This is 4 and 5 to 6. 5.
In Kruskal's algorithm, you start with the vertex. Obviously, you start with the minimum edge only. Let's say this is the minimum edge, right? And afterwards, the algorithm changes and it says take these two vertices and take the edges that are directly connected to these two vertices. So the edges that are directly connected to these two vertices are this one, and this one, right? And then you take the minimum of these 3 edges. So this is 3, this is 2, this is 3. That means next up you should be choosing this one.
Ma'am, 3 to 6 is 2. 3 to 6 has weight 2.
Okay, this one's also left. Okay. So first you choose the minimum weight edge, and then you take the vertices and see every edge that is directly connected to those two vertices. We have 2 vertices, and you check every edge that is directly connected to these 2 vertices, 1 and 2, which is this edge, and this edge. And then you find out the minimum cost edge, minimum weight edge, which is this one, and you draw this one. Then this vertex has also been covered, so you take the edges that are directly connected to 3. So this edge, this edge, this edge, and this edge, right? So the covered edges are this has already been done. This. Now you take the minimum out of all of these edges that we have marked. So the minimum then is this.
3 to 6.
3 to 6 is the
3
minimum.
to
one.
6.
Then 6 has been covered, so you take this one. That's it. And you take the minimum out of all of these edges, out of all of the edges that I've marked so far. So the minimum of these is then 2 has been covered, and then the next minimum is you can take 3, you can take any of these, right? This one, or this one. So Let's take this one. For a change, let's take this one.
6 to 7.
So this doesn't change anything. No? We have edges here that the ones are covered already. Let's take this one. So this and then the other. Now it becomes the same as that only. Let's not take this one. Why I'm not taking this vertex is because if I take 7 vertex, then 7 gets covered, and then you mark the edges that are directly connected to 7, right? Which is this edge and this edge. And I don't want every edge to be marked because then it will just become like Prim's algorithm. So let's take something else. Let's take 4. This is 3. Then these edges have been done, and out of all the ones that have been marked so far, you choose the minimum. Then you take the next minimum here. Then so every vertex that's covered here, you just need to mark the edges outgoing and incoming. There are no outgoing incoming edges here though. So you mark every edge that is directly connected to that vertex, and you write the minimum of them. So in the previous one, what we did was we simply just used to rearrange the edges in ascending order of their weights, and then we just used to draw those edges in that order only, such that they're not making any cycles, right? That's what we used to do in the previous algorithm. In this algorithm, you start with one edge, and then the vertex that are the vertices on that edge, you see every edge that's outgoing that is directly connected to those vertices, and then you choose the minimum weight edge out of those edges. So when you've reached only this point,
Ma'am,
now let's say you have 2 here. Just one second. Let's say if this is 2, and you're doing this thing. So when you start doing this algorithm, you've only covered this thing. And then next up, because you can take up this and this one. Yes.
actually you have actually this algorithm is pre, the
Okay, this
upper
ones
one.
are they opposite?
Yeah, they are opposite. Primes.
This is Prim's algorithm, and this one is Kruskal's.
Ma'am, I got confused.
Confused what? In
Ma'am,
the names or okay, in first algorithm, what you do is, let's say you have these edges, right? You just arrange them in ascending of the weight. So the least weight is 1, 2. Then we have 2, 3. And 2, 3's weight is the same as 3, 8. Yeah. Then for next up, you should have 1, 3. Then 2, 4. 5, 7. Then 6, 7. All are done, right? 1, 2, 3, 4. And you arrange them in this order. I'm not writing all of them. And then you start drawing these edges in this order only. So first you draw this edge, then you draw this edge, then you draw this edge. Start drawing these edges till you find a spanning tree. And make sure that there are no cycles because you're trying to make a spanning tree. So there should be no cycle. So if this edge is forming a cycle, then you should not choose this edge. Else start choosing the edges in this order. That's Kruskal's algorithm. Is that okay?
yeah, ma'am.
Now in Prim's algorithm, what we do is we don't arrange them and start putting them one by one. What we do here is we start with the minimum cost one, obviously, the minimum weight one, which is this. And then instead of going to the next minimum one, we take the ones that are directly attached to this. So directly attached are these ones, right? This one, and this one. So you take the minimum out of these 3. But in Kruskal's algorithm, you used to take the minimum out of all of the remaining edges. In this one, you take minimum out of only these 3 edges, right?
So, ma'am, we explore it first, right?
Explore it.
Yeah, means under that vertex, whatever is coming, the lowest of them only we are
Yeah.
taking.
In that sense, you explore these 2 vertices first, right? and then you choose the minimum weight edge.
Got it, ma'am.
So even if you have a 2 here, you can't choose this yet. Why? Because this vertex has not been covered yet. You can only choose this edge when this vertex is covered or this vertex is covered.
Okay, ma'am.
So it's like unlocking these edges. When you have 1, 2 here, this edge, and this edge, these 3 edges get unlocked. 1, 2 is already there, right? So 1, 3, 2, 3, and 2, 4. These edges get unlocked when you have 1, 2 as edge. For this one, these edges get unlocked, and then you choose the minimum one, and then you add. Let's say you're adding this, right? Next up, you add this to your tree, and then these become unlocked. So this one becomes unlocked, this becomes unlocked, this becomes unlocked, and this becomes unlocked. Now you can choose out of all of these edges that are unlocked. And you continue in this manner till you find your minimum cost spanning tree. Or in simple
Madam?
words, you find your spanning tree. That's all.
One confusion. Like
Yes.
if you take 7 to 8 as a 2, it's a weighing factor right now. But
Yeah.
in the previous algorithm, can we take like 7 to 2 in the first or second step because we did not come to 7, right?
Yeah, if you had 2 here, you would be choosing this edge first.
Like, so from 6, how can I choose directly 7 to 8, madam? That's my confusion. I'm clear.
In this algorithm in Crystals, if this is your graph, what you do is first you draw the minimum, the least one,
Yeah.
which is this, right? 1 to 2.
Yes, that is
This has
clear.
weight 1. Then you go to the next least ones. So it's this one, and this one, right?
Mhm.
So you draw this one, unless they are making a cycle. So draw every one, unless they are making each one of these, you have to draw, unless they are making a cycle. So
Yes.
if this was also 2, you wouldn't choose this one because it's making a cycle.
Ma'am, if
Then
2
we
to
skip edges.
3, if 2 to 3 have 3, then we can choose 7 to 8.
This was, you're saying if this was 3.
Yes, ma'am.
If this was 3, then you choose. Okay, if this was 3, then you wouldn't choose this. After this edge, you choose this edge.
1 and 3.
3, 8. You choose 3, 8, and you'll choose 7, 8. What is this? This is 6, right? 3, 6, and 7, 8.
Okay, so it can be still disconnected at the first.
Yeah. The finally it should be connected. That's all.
Okay. Yes, ma'am. Thank you.
But ma'am, how 3 unlock if we are not connected?
The unlock one is for this Prim's algorithm. This is Crystal's algorithm.
Okay.
Are both the algorithms clear?
Yes, ma'am.
Yes.
Ma'am, all vertices should be covered is the rule for both algorithm, right?
Yeah, because when the algorithms are just ways to find minimum cost spanning tree. Our ultimate goal is to find minimum cost spanning tree. That means it should be a tree. That means it should be connected and it should be a spanning tree. That means every vertex should be covered.
Okay, ma'am.
Ma'am, can you complete the example for Prim's algorithm?
Yeah, sure.
Ma'am, in the
Start from
lecture,
here.
there were also mention about the minimum separator lemma. What is this?
I'm not sure. I'll have to check. It must be a lemma, and lemmas are basically you have to. It's like a proof thing, like you do theorems. It's not exactly a theorem, but it's similar to a theorem, and you don't need to do theorems. If it's been given in the lectures, then you can give it a read or you can read or study it, but that's not needed.
Okay, ma'am.
Okay. So if you really want to discuss that lemma, what is it called? What's the lemma called?
Minimum separator lemma.
Minimum separator lemma. We can discuss that in the next class. Is that okay?
Okay, ma'am.
Ma'am, the time is end.
We have some time left. So in this one, so you choose this one first, then you choose this. Then next up, because these has been unlocked, this is very messy. Become unlocked, then you take 2 here. So now you've written 3, so these become unlocked then. So out of 4, 5, 2, 3, 4, 3, you have to choose the minimum. So the minimum, you can't choose this one because it's forming a cycle. So you should be choosing this one then. Then if you choose this one, then these become unlocked, right? Only this one becomes unlocked, and this has already been chosen. So now you have to choose from this edge. These one have been done already. This edge, and this edge. So you have to choose out of these 4 edges. And the minimum one is this.
3 to 6.
Ma'am,
Yeah. And these
ma'am,
two become unlocked. Yeah.
ma'am, we not take 4, I think. First we cover all minimum, and then we see 4 is connected 2 and 3 both. Then we take the minimum one.
No, you directly take the minimum from the ones that you have available. So firstly, you started with these, so only these 3 edges were available, or you can say unlocked. So you choose out of these edges, and then a new vertex 3 gets added.
Yeah, ma'am. I'm saying we first take the minimum line, or we can say minimum,
Yeah, so we're
like
taking
1,
minimum
2.
edges only. 3 is one of the minimums here.
But ma'am, we don't know the 3 is minimum because we only unlock 2.
Basically, ma'am, from 3
Well,
to 6 it is 2, and from 3 to 4 it is 4, and 2 to 3 is 3.
that's the difference between Prim's algorithm and Kruskal's algorithm. You don't go in the ascending order in this case.
No, that's okay, but the edges connecting from with 3 have 2, 4, 5.
Okay, wait. Let's do this again. Have this thing. Then these 3 get unlocked. You choose this as next. Then, okay, so these one have already been unlocked, right? So this is these 2 and these 2 and this one. So minimum out of these is that, yeah, right. Then it's this one, and then these get unlocked, this one and this one. This is not yet unlocked. So you choose the minimum out of all of these. It's this one, right?
Yeah, that's what I'm saying. Because
Okay.
then
Understood.
I
I
know
understood.
okay.
We'll be taking this. I couldn't actually see that this is also one of the unlocked edges. That's why I took this 3 one. Okay. Then this is the next one. And then out of the remaining ones, because this is a closing edge for a cycle, can't take this one, can't take this one. So the next minimum would be this one. And then these two get unlocked. Now all the edges are unlocked, so it becomes, when your all edges are unlocked, it's similar to Kruskal's algorithm only, right? Is that understood to everyone? When all your edges are unlocked, that means you can choose any edge now, as per the ascending order, obviously. So if all your edges are unlocked, then your Prim's algorithm is the same as your Kruskal's algorithm. Now afterwards, this and Kruskal's algorithm is the same way. They both work in the same way because all the edges have been unlocked in Prim's algorithm. So next
Then
minimum
we'll
edge
take
would be,
7 to 8.
yeah, next you take 7 to 8. This one. Then next you take, can't take this one, this one. Next is
6 to
2
5.
is already taken. 6 to 5, and this is also there. So you can take this too. What have we taken in the previous one? You can take this. This also has weight 4, right? You could have taken this too. That also works. That's also fine. And then I think we've got our spanning tree. This is our spanning tree, right? Now this is the
Ma'am, what is
spanning
the
tree.
value of 7 to 5?
7 to 5, we're not even using it. Let's just keep it as 6. Or let's keep it
Okay,
as
ma'am.
something greater than 4 because we're not using this edge. In the previous one, we chose this to be 3. Now, if you take this to be 3, then you'll have to take this edge.
Ma'am.
Yeah.
I understand this graph, but if we don't put the weightage like 1, 3, 2, 3, then what will be the impact?
If you don't put the weights here, then how would you? We're trying to find minimum cost spanning tree, right? A spanning tree that has minimum cost, and these are your costs. Now, if you remove costs from here, then how would you find minimum cost? Then there will be no concept of minimum cost spanning tree, right?
Okay.
Ma'am, because
Okay.
you are finding minimum cost, you have connected 7 to 8, and again you are connecting 7 to 5.
Yeah.
I understand that all the vertices must be covered, but is that necessary that like at last we have to connect all, right?
Yeah, we have to connect all the vertices. This should be a tree, that's all.
Okay.
And it should have all vertices in it.
Okay.
Ma'am,
Yeah.
one small confusion, please. Means how we calculate the cost, this like 3 and 2, how we do? Means the edges, incoming edges.
No, this will be given in the question. You don't have to worry about the weights. The weights, this is what you're talking about, right?
Yes.
This will be given in the question.
Okay, ma'am.
And then your minimum cost. So this is your minimum cost spanning tree. And your minimum cost is this. Now, when you do this via or using Prince algorithm or Kruskal's algorithm, your minimum cost is always the same. You can get different trees, but there could be more than your minimum cost spanning tree is not unique. Now, if you had this as 3 only, if you had 3 here, then it's not unique, right? You can have this as minimum cost spanning tree, or you can also have this tree. This is also a minimum cost spanning tree, right? So minimum cost spanning trees are not unique. But your minimum cost is unique. That means no matter which tree you choose, which minimum cost spanning tree you choose, your minimum cost will turn out to be same. So even if you use Kruskal's algorithm, then also you'll get the same minimum cost. If you use this algorithm, then also you'll get the same cost. So the minimum cost remains same, but your trees can change. Is that okay?
Yeah, ma'am.
Yes, ma'am.
Yes, madam.
6, 9, 12, 13, 14, 15, 16. So 16 is your minimum cost in this for this exam. Then we have the shortest path problem. Shortest path problem for graphs, for weighted graphs only. This is also a problem for weighted graphs. In shortest path problem is basically, let's just say you have a graph, and let's say you have this graph. And you have weights here, let's say 1, 2, 3, 4, 5. So you have to find the shortest path. Now the shortest path means when you need to find the shortest path, let's say if you don't have weights, then you simply find it from here, right? Like from V1 to V3, your shortest path, or even if you have this. Now, if you were to ignore the weights, then the minimum, the shortest path from V1 to V3 will be V1 to V2 to V3, right? Let's take 3 here. And let's take 1 for both of these edges. So this will be, if you don't consider the weights, then your minimum weight, the shortest path from V1 to V3. Is this one, right?
Yes,
But
ma'am.
if you will consider the weights, then this is not the shortest path, right? Let's say if you have to go from this place to this place, you get charged 1k rupees. And from here to here, you get charged 3k rupees. And from here to here, 1k, 1k. Now, if you will go via this path, this will be 4k in total. And if you go via this path, or let's say this is 1 kilometers long, this is an easier, better example to understanding. So this is 1 kilometer and this is 3 kilometers and this total is 4 kilometers, right? And from this path, it will be 3 kilometers. That means now your shortest path becomes V1 to V2 to V4 to V3, right?
Yes, ma'am.
So when you don't have weights on your graph, you don't need algorithms. But here you need algorithms to find the shortest path from. So when we talk about shortest path in weighted graphs, that's what we mean. I hope everyone's clear with what a shortest path exactly is in a weighted graph.
Yes, ma'am.
Then
Yes.
let's come to the algorithm that helps you find the shortest path from a source vertex. Source vertex means, let's just say you've taken vertex 1 and you need to find the shortest path of every other vertex from this vertex V1. How do we do this? Let's just consider this graph only first. You first write all the vertices here, which is 1, 2, 3, 4, and 5. Then you initialize things from here, so you keep 0 here and infinity at all of these vertices. So you consider the distance of all of these vertices to be infinity. So for the first one, you have this at distance 0 and all the others at distance infinity. This is how you initialize things. Then when you come to V1, you see that
We
this
unlock
distance
V2.
is 1. Yeah. Yeah, you can say that we unlock V2. This distance becomes 1. So here you write the vertex. So it's from vertex V1, or you can say just 1. Let's use V here so that there's no confusion. This remains 0 only. And remember that we have to find the shortest path. That means we have to find the shortest this thing, right? This sum should be shortest. Then we come to V2. So this is directly connected to V1. So we write a 1. Every vertex that is directly connected to V1. You've started from this one, right? This is your source vertex. Every vertex that is directly connected to V1, you write those distances here. So the distance here is 1. You write 1 here. And then that's it. Others remain at infinity. This is directly connected to it. So this becomes 1. This becomes at distance 1 and the others remain at infinity. Now this gets unlocked and you write V2 here. This distance has been fixed. So the minimum distance for this, the shortest path is 0. Shortest path for V1 has been from V1 to V1, that's 0, right?
Yes, ma'am. V1 to.
So we've discovered this to be 0. Then coming to V1 to V2, next. Now what we do here is, in this one, it's actually easy. We shouldn't be taking this example because it's not a good example to understand Dijkstra method. This is called, the method that we're discussing is called Dijkstra method, Dijkstra algorithm. Let's take some other example in which the algorithm is properly used. So let's take this example. Let's say you have vertex 0 here, 1 here, 2 here, then let's say you have this here, 3, then you have 4, let's take this one. Let's take the weights to be 1, 2, 2, 4, 3, 5. First, you write all the vertices here 0, 1, 2, 3, 4, 5, 6, and 7. We don't have 7. And let's say this is your source vertex. You've taken this to be the source vertex. So you write 0 here. And then you write the ones that are directly connected to it. So the distance, first, when you initialize things, you keep everything to be the source vertex to be at 0 and every other vertex to be at infinity, right? And then in the next step, you take the source vertex, this vertex here. So this distance gets fixed. So minimum distance, the shortest path for 0 gets fixed, which is 0. And we discussed why it is 0, because you're going from 0 to 0. That's why it's 0. So this is now fixed. And you write B0 here, or 0, just 0 here. Now this is the selected vertex. It is kind of unlocked. This has been unlocked. So you can go to these two, right? So the distance from 0 to 1, you change the distance. This is
1.
0 only because this has been fixed. Distance from for 0 has been fixed, right? So we don't change this. And for 1, you get 1. For 2, you get 2. And for others, let's take 3.
Are locked.
And the other ones remain at infinity. So, because you've unlocked only these ones, 2 and 3. They are only the ones that are directly connected to the source vertex and the ones that have been unlocked. Only those get unlocked. So if you are on this vertex, these two get unlocked. So we write 1, 3 here and others remain at infinity. Now these two have been unlocked. 1 and 2. So out of these two, you choose one vertex depending on which one has the minimum weight. So this one has the minimum one here. So you choose the minimum for these two. The minimum of 1 and 3 is 1. You choose this one. And you fix this. So you take the next vertex that you take up is 1. And you fix, now this was already fixed. This weight was already fixed. And the minimum distance for 1 has been fixed now. That means minimum distance from source 0. Minimum distance 0 to 0 is obviously 0. And then from 0 to 1, it has been discovered to be 1, right? So once you fix a vertex, that's what you do when you choose the minimum, because you've chosen the minimum of these two to be this. So when you choose the minimum one, that gets fixed. Now you can't change these entries later because you've chosen this vertex. This kind of becomes frozen. That means you can't change. Now the minimum distance has been found to be 1. You can't change the minimum distance here.
Ma'am,
I'll tell you what I mean by changing the distance.
Second column.
Ma'am, I have a doubt.
For 2
Let
and
me
3,
just first
if you
do
count
this.
0, 1, 2, 3, if you count only 3 values, is there 4 values should be there, right?
Ma'am, I have a
So first you chose the minimum. So first you chose the shortest path, or you can say the minimum distance for 0, that was 0 only. Then you chose it for 1, which is 1 here. Then you choose, this has been unlocked, right? So you find the minimum distance of the ones that are directly connected to this one, which is this
My
all,
doubt is how it is 3, like how the distance of
because
2
this
is
is at
3.
3. The weight here is 3. We're just
Okay.
writing weights here, that's all. You start
So,
with this vertex.
yeah, so the vertices we unlock, that is, we'll take the value, and other vertices should be infinity.
Yeah.
Okay, ma'am.
Now this is the selected vertex. I've written 1 here. That's why I've written it. The selected vertex is 1 this time. So the distances that you should be changing from infinity to something else should be these ones, right? Because they're directly connected to 1. So you can change this, you can change this, and you can change this too, because this is also directly connected to 1, right? So if you do this one, you will get that this is at distance 1, right? This is at distance 0. The distance for this has been decided as 0. This is at distance 1. This has also been decided here because we fixed this distance. Now for these distances, it is 1 plus 2. 1 plus 2, so this should be 3, right? So this is your fourth vertex is at distance 3. Then your second vertex is at distance 1 plus 2, 3. And you already have 3 here. So let's say if this was 1, then you will have 1. And from here you will have 1. So it will be 2. And directly from here you have 3, right? So you already have 3 here. If you find something smaller than 3, you replace this thing. If you find something bigger than 3, then you keep it as 3. Is this okay? So if you have 1 here, you start with this one and you go to 1 plus 1. So this becomes 2 and it already has a weight 3 here. So you have to choose the minimum between 3 and 2 because you're trying to find the shortest path. So in this case, it should be 2. Is this okay?
Yes, ma'am, it's okay.
Okay. If there's any doubt, any confusion, you guys can ask. And then next, we've done 3 is remaining, right? So this is 1 plus 3. So this will become 4. And 4 is less than infinity, so you should replace it. Okay. And then the other ones, because they are not directly, they don't have a direct edge with 1, so they remain at infinity. 5 and 6 do not have a direct edge with 1, that's why they are at infinity. Then you choose the minimum of these 3, because this has already been fixed, right? This we've already fixed. Shortest path of 1 from 0 we've already fixed to be 1, so we will choose out of these ones. The next one should be 2. And then you should be choosing this vertex, second vertex. Should I write V here to avoid confusion? So this is V2 vertex. You choose V2 vertex here, which is this. Then you choose, then you look at the vertices that is directly connected to. So it is only directly connected to third one, right? So you do 3 plus 4. This is 3 and this is 4. So it becomes 7. But 3 has already, what's the weight for 3? It's the shortest distance for 3 is 4, right? And 4 is less than 7. So you should be keeping this as 4. We're not replacing it with 7 because the shortest path is 4. So we'll keep it as 4 here. Is that okay?
Yes, ma'am.
So we are getting 7 from here. We're getting 7 from this and this. But we're not choosing that. So this will remain 4. And 3, okay, that's all, right? And others remain the same. This remains 3 only. Both of these remain at infinity only.
I
Then
think
we
not
come to,
7, I think 6.
it's 3 plus 4, right? So it's 7.
Ma'am, we take
Or if you
0
do
to
this
1,
one, yeah,
1 to 2.
you're right. Thanks. You add to this one, right? To the minimum one chosen. 1 second. To avoid confusion, let's just not look at the graph. Let's do it directly from this table. When you have, we were doing V2. Next vertex we chose was
You'll
V2.
take the last fixed value, right? The fixed value will be
Yeah,
2
we
for
take the
this.
last fixed value. So it's 4 here. For 3 vertex from V2 to V3 if you have to choose. So you take the one that was previously fixed. So the last fixed value is 2, right?
2.
We're fixing 2 here. In this one. Or not here. Let's just mark 2 here. In this iteration, you have fixed 2 here. And you're taking this vertex, right? V2 vertex. So you should be adding 2 to all of these. So basically what you do is you add 2 to the previous one. Or so this one gives you 4 from V2 to V3. The direct one gives you 4, which you have previously. And this one gives you 2 plus 4. So it will be 6. And next up, we choose the next fixed one should be this one, right? So we should fix V4 here. 0 has been fixed as the shortest distance for 0. Shortest distance for 1 is
V3,
also fixed.
V3.
2, is it?
V3, ma'am, in row.
No, this is the shortest distance. We should be choosing V4, right? Three is corresponding to the fourth vertex. 4 is corresponding to the third vertex. The minimum distance now is out of these two, you have to choose 3. That means you have to choose fourth vertex. And you have to, so when you add things, you have to just look at the weight that you have at 4. So at fourth vertex, you have, or the distance till fourth, the shortest distance till fourth vertex. So your shortest distance till fourth vertex is 3, right? The shortest distance till fourth vertex is 3, and now you should be adding things to 3 only. So till this is your fourth vertex. The shortest distance till 4 is 3. Shortest distance till 2 is 2. This is 3. So now you will unlock these ones. This edge, and okay, these two only. So for you to find the distance from 5 to 6, it should be 3 plus 1, right?
4.
So it will be 4 here. These remain same because they have been fixed. And for B3, because you don't have, if this was an opposite edge, let's say if you had this edge and this was 1, then what you do is till 4 you had 3, you add 1 to it, so you will get 4 here. And you already have 4 here. Let's say this is a 0 weight edge. Then till fourth point, you have 3, right? Because your shortest path till 4 is 3. So till 4 you have 3. And 2, 3 you add 0. So if you add 0, you will get 3. That means till V4 you should have 3. And the already written one is 4. And 3 is less than 4. That's why you should replace 4 with 3. You should take 3 here. Fourth one is already 3 and it has been fixed also. Then for the fifth one, you should be taking 3
Fifth
plus
one is
1,
4.
4. And for this one, you should be taking 3 plus 2, which is 5.
5.
Then you fix the next smallest one. So these have been done, right? These have already been done. This, and this. The smallest one here is 3 this time. So next vertex you choose is B3. These are not going to change. The fixed ones don't change. And this is also fixed this time. Now you only choose these. But they don't have a direct edge with 3, right?
Yes, no direct
Yeah,
edge.
you don't have a direct edge to B6 and B5 from 3. So you should be keeping. So the distance from basically the distance from 3 to 5 is infinity. And between infinity and 4 is the lesser one. So you should keep it as 4 only. Same goes there. Should keep it as 5.
Ma'am,
Yes.
if we get like two weightage of the same size, like 3 and 3, so like which one do we choose?
Choose whichever you want.
Okay.
And then the next up we should be, because these are already fixed, then the next minimum weight is out of these two, it's this one, right? So next up you should take B5. These are already fixed weights. And this time you fix this weight. So you have fifth vertex this time, and the weight here is 4, right? So till this you have the shortest, not weight. If I'm using the, I've used this word a lot of times. This is not weight, this is your shortest distance, right? So the shortest distance till this point, 5, is 4. That means if you have to do, and you don't have an option to go here, right? From 5 to 6, it's infinity only, right? The distance from 5 to 6 is
Yes.
infinity because they
Yes,
don't have a
ma'am.
direct
Opposite
edge.
direction.
Yes, ma'am.
That means now if you add 4 to infinity, it will remain infinity. There's no point. And 5 is obviously lesser than infinity. That means you should be keeping 5 here only. That means all your distances have been fixed. Next time this gets fixed. 0, 1, 2, 3, 3, 4, and 5. That means the shortest distance from 0 to 0 is 0. Then the shortest distance from 0 to 1 is 1. From 0 to 2, it's 2. So these are the shortest distances from 0 to all of these. Is this clear to everyone? The Dijkstra algorithm?
Yes, ma'am.
Okay. If there are still doubts in this algorithm, we can discuss that. We can do one more example on this tomorrow. And we'll do the next algorithm, like the last algorithm that we have. Do you have anything left from this week other than Bellman-Ford and Floyd-Walshall? Do we have Floyd-Walshall in syllabus?
Ma'am, are there different methods in this Bellman-Ford algorithm? Because when I search for it online, I see people solving it in different methods.
Yeah, there are no different methods to it, but
What is this
it
method
is
called?
actually done. This one, the one that we discussed,
Yeah.
this one's called Dijkstra algorithm.
No. See, the way you solve it, if you use online materials or watch YouTube materials, they
Yeah.
solve it in a different way than what way the way you solved it.
No, but the Dijkstra algorithm is this only. It's this. What they do is they try to find the shortest path. So either sometimes you don't even need this table, but it's just easier to keep a track of everything. That's why we have this table here. The Dijkstra algorithm done with in some other manner somewhere else.
I don't know, ma'am.
It's this only. Dijkstra algorithm is this. And then Bellman-Ford, it's Bellman-Ford and this Floyd-Walshall we'll discuss tomorrow. These two methods.
Can we
are
solve
next.
one more example of Dijkstra's algorithm tomorrow?
Yeah, we can do one more question. We'll do one more on this Dijkstra algorithm.
Ma'am, just a question. So like these vertices has weightage, the edges, right? So
Yeah.
like these weightages like of what?
Weightages, it could be anything. That these weights represent now. When you draw a graph, your vertices represent something and edges represent something, right? So in a similar fashion, the edges also, the weights also represent something. Like if you take these to the airports, then these could represent the fare, right? To go
Okay.
from this airport to this airport, the airline fare.
Okay.
Or
Got
this could be
Like, ma'am,
distance
we
from,
use as data. Like,
sorry, what?
weight is data. Weight.
Yeah, it's data
Um,
only, and it depends
Ma'am,
what kind of data you're taking, but it's called shortest distance.
Okay.
Though
Got
it's
ma'am,
not always distance. This doesn't always mean distance. Yeah.
in the lecture, the way you solve this problem, it is Boltzmann-Ford algorithm.
Oh no, this is Bellman-Ford's algorithm. Okay, let me just tell you the main difference between Bellman-Ford algorithm and Dijkstra algorithm. This
Ma'am, the problem is I watched this already. I finished this like 3-4 days before itself, but it's all a mess in my mind. I'm not able to properly recall everything and differences and how the thing is working. And when I try to watch online YouTube videos, everything is different, done in a different way. So I'm totally confused.
In the lectures now, they have just written in the 3 columns. First is vertices. Second, they have written the distance, and third, in the third column, previous vertices, like that. And
in
this way, all
Bellman-Ford, I can just tell you the main difference between Bellman-Ford algorithm and Dijkstra algorithm quickly. So in Dijkstra algorithm, what you do is when you are at this vertex, only these two get unbound, right? And then you write the distances, the shortest distances from there. And your shortest distances are these, which keeps getting updated, right? That's what you do in Dijkstra method. But when you are using Bellman-Ford method, you test every vertex. Like this time, you've only taken these two, right? But because they are only directly connected to zero. But in Bellman-Ford algorithm, you take all of them. And then you find the minimum distance of all of these one time. That's called one iteration. And then you do it again. And Bellman-Ford is basically for, it gives you the same answer. Bellman-Ford and Dijkstra algorithm gives you the same answer for positive weights. So no matter what you use, okay, let me just write it down here.
can you
If you
recheck?
have,
So,
I
ma'am,
think you were telling
in Bellman, we have to keep checking the updated vertices. Means if the vertices are getting updated or not.
and can you please recheck?
Dijkstra algorithm,
I think you are telling the opposite.
no, in Dijkstra algorithm, what you do is this is for positive weights only. So when you have positive weights, that's only when you use Dijkstra algorithm. So if you have negative weights, you can't use Dijkstra algorithm. Then is when you use Bellman-Ford algorithm. So this algorithm is for negative weights. It's also for positive weights, also for negative weights. It's for both. Works for both type of graphs, but this one Dijkstra algorithm only works for positive graphs, positive weight. If you have, if instead of 1 you had -1 here, you couldn't use then you can't use Dijkstra algorithm. You have to use Bellman-Ford algorithm. And in Bellman-Ford algorithm, you complete, like in this one you were doing 1. In Bellman-Ford algorithm, you take the edges and then you take 1, and you take the minimum distance from each of from this vertex to each of these vertices. Like this one will be 1, and then in this one it was 3 here, right? So it will be 3. Then here you'll have, for this one you'll have 1 plus 1 2, and for this one, so basically they work the same way when you have positive weights. Work the same way and you get the same answer when you have positive weights.
ma'am,
But
like
it
we
is
have.
different when you have negative weights.
So, ma'am, as you said that we can use Bellman for negative as well as positive weight.
Yeah.
So, is there any particular case where we have to look for Dijkstra algorithm, or we can use Bellman for every type
You
of
can
weight?
use Bellman-Ford algorithm everywhere, but in Bellman-Ford algorithm, you repeat n-1 iteration, so it might take you some more time to do it with Bellman-Ford algorithm.
So there are some cases where Dijkstra algorithm is much more beneficial than Bellman.
Not as such. It's for, like, if you have V1 and then V1 is connected to, let's say, 10 vertices, and then V2 is also connected to all the other 10 vertices. V3 is also connected to all the other 10 vertices. then this is the Bellman-Ford algorithm is going to take a lot of time. Because each time, in each iteration, you relax this thing that we do. For vertices, when you change these, when you take minimum of the weight that's already, or minimum of the distance that is already at the vertex, like this one, and the other one that you get from other part, and you choose the minimum of these two. That's called relaxation of edges. So when you relax edges, you relax in Dijkstra algorithm, you only relax the edges that are directly connected to these vertices, these unlocked vertices. But in Bellman-Ford algorithm, in each iteration, there are n minus 1 iteration. If there are n edges, n vertices, then the number of iterations is n minus 1.
So in Dijkstra, if we use one vertices, then its value got fixed. But in Bellman, it can be updated in the next step.
It can change. You will be completing. Sometimes it gets done before n minus 1 iterations, but maximum number of iterations that you can do Bellman-Ford in is n minus 1 iterations. So if you have, so you repeat the same thing n minus 1 times. And for
It
each
is
vertex, in
also
each iteration, you visit every vertex and change the distances each time. That means you relax edges each time. That's why it's a little longer method.
ma'am, it's also changing Dijkstra method, but in Bellman-Ford method we have more edges. That's why we update in
What?
We update in alteration, extra alteration.
In each, it's not really necessary that after each iteration things will get updated. Sometimes you get done with just 2-3 iterations, and then you don't need to do them anymore because your weights come out to be same and same again. So after some iterations, the weights become fixed. They don't change then.
Okay, ma'am. If my second step and third steps are the same, so we don't have to check further.
Then you don't have to go further. That means all of your other steps would also be same.
There isn't any chance that in the further step it might get changed. It will always be the same if the two steps are the same.
Yeah.
Okay.
Okay. We wrap up this session here.
Okay, ma'am. Thank you.
Thank you, ma'am.
Ma'am, will you explain this Bellman-Ford tomorrow?
Yeah, we'll do Bellman-Ford and the Floyd-Warshall one tomorrow.
Okay, ma'am. Thank you.